So this is a pretty, I think, pretty remarkable result. And so this is an example we call a variational result. And so there's another really common major example of an infinite dimensional problem that can be reduced to a finite dimensional one. So here we're saying that the solution to this problem lies in a finite dimensional subspace. That subspace is the space spanned by natural third order splines. It has dimension n. So once we know that, once we know this fact, to solve this, we can just plug in f equals the sum of beta j gj for those basis functions, and then we can solve for beta, and then we have a solution to this infinite dimensional problem. So we'll do that in a second. Before I get to that, what is the other major example of an infinite dimensional problem that I can reduce to finite dimensional form? You guys would have probably seen it in 701. Yeah, reproducing kernel Hilbert spaces. That's, in some way, these are actually kind of parallel results. And I have the proofs for both in the notes. The proof for the RKHS case is actually, in some cases, it's simpler than this proof. It's just a few lines. But it also requires you maybe believing or buying into some properties of the RKHS framework that are not as apparent. This proof is really from first principles. This proof is just integration by parts. You have taken calculus. Once you learn integration by parts, that's it. You can prove this. All right, so let me tell you what we get from this fact first. And then I'll maybe see whether we want to. So this would have been better to mention early on. But that means that we're encouraging the fit to be smoother and smoother. We want the second derivative to change less over the input plane. So it's going to be smoother for larger lambda. As lambda gets smaller, we don't care as much about how wiggly the second derivative is. It can change a lot as we move over the input space. And we care more about minimizing the squared error to y. So lambda controls the complexity of the fit. Larger lambda is lower complexity. So it's also given. It's not given in the sense that we would know what it is for a particular problem. That still needs to be tuned. But with respect to this minimization, it's fixed. And so the solution is theta hat equals G transpose G plus omega, I think lambda omega, inverse G transpose y. So if you don't believe me, then just take a derivative that says equal to 0, and you'll see that's the solution. So once again, if I ask for the fitted values, if I ask for y hat, then that's just given by G times G transpose G plus lambda omega inverse G transpose y. So it's just a matrix times y. Again, it's a linear square. All right, given how little time we have left, I think I'm actually not going to go through the proof. It's on page 9 of the notes. So there's a bullet point that says, remarkably, it so happens, blah, blah, blah. 2 paragraphs down starts the proof, and it lasts for about a page. And it's really just, like I said, it's just some calculus, integration by parts. Yes?
I have a question. So for using these bases, it is quite clear that this omega ij will be finite because we are integrating this over treatments, but over finite x. But if we are using the commutative power basis, then is it obvious that this omega ij will be finite?
It's a good point. It's not at all obvious. I'm also being sloppy because even in the original problem, we should have just written bounds A and B that go from before the leftmost point and the after rightmost point. But otherwise, it wouldn't really be a very interesting problem. So that we put those bounds there, I mean, if you know, if you observe data in some interval, you just take any containing interval a, b, and then that defines the problem. So this ends up just being integrated over those same bounds.
But if you're using natural spline basis, then outside of this A and B, wouldn't the second derivative, which is a cubic smoothing spline, wouldn't that be just zero? So
Yeah, it would be. So that in fact, you can already tell why it has to be. Well,
so you don't actually need the A and B for the different basis function.
yeah, it's a good question. So if we didn't put the a and b there, you're right. We'd be forced to make the k plus first over second derivative equal to 0 beyond the leftmost and rightmost point. So that would already tell you that we're looking at a natural cubic spline, or natural spline is ordered k. So I guess we don't need those a and b to begin with. But when we well, okay, I mean, if this is the basis for natural cubic splines, it also has to have the same property, right? It's going to have 0 derivatives beyond x1. That's a better way of phrasing it. What ends up happening in the proof is that, yeah, you just replace all these intervals with actually an interval from x1 to xn, which I called a and b in the proof. So I could go on about splines. I'm going to try to wrap up with splines so we can talk about linear smoothers. But I'm going to talk about one more thing, which is the Reinsch form of smoothing splines, because you have a homework problem on that. So you'd probably be mad at me if we didn't talk about it. So I have these fit values, right? They're G times G transpose G plus lambda omega inverse G transpose Y. And there's a nice way to rewrite this so that you can see a little more explicitly what the smoothing spline is doing. And it's kind of like the kernel trick. So it may remind you a bit of that if you've seen that with RKHS stuff. And all we do is that we write in here, I think I called it N in the notes, by the way. So I hope you're not terribly confused by that. But yeah, in the notes, G is N. I just use that for natural spline. So we write that as this. So what we do here is that we pull out, from this inside guy, we pull out a G transpose. So we have to pull out the same thing here. Okay, that's an invertible matrix, because remember it's n by n and it has dimension, has column rank or dimension n. Omega G inverse G inverse G transpose 1. So all I've done is I've taken on the inside, I've just taken out a factor of G from the left and a factor of G from the right. And I've had to multiply by G transpose inverse and G inverse here to make up for that. And so now I have the inverse of a product of 3 matrices, each of which are invertible. So I can just reverse the order and take the products of their inverses. So I get G times that guy, G inverse, times I plus lambda G transpose inverse omega G inverse here, get G transpose inverse G transpose Y. Those cancel, right? And so all I get is I plus lambda times, I'm going to call this matrix K. K inverse times Y. Where K is this matrix. This is what happens when I take the natural cubic spline basis matrix, take its transpose inverse, this kind of cross product matrix, the inverse of the natural cubic spline basis matrix. So this already looks like what we do with reproducing kernels, or Mercer kernels, right? Because the form of the fitted values there are very similar to this. It looks like this, and that's why I chose the K there. But it also tells us something about the way that the kind of action that smoothing splines have on the fitted values. And so, in particular, if I take a singular value decomposition of K, well, let's just write, or I guess it's an eigen decomposition because K is symmetric. Okay, let that be an eigen decomposition of K. Then this guy has the following eigen decomposition. Right? Because U's orthogonal. And so the eigen decomposition of this is now just this. That should be a D, sorry. So D is diagonal, U has orthogonal columns. And so when I write down the smoothing spline fitted values, so I have a y hat which is equal to just this times y, right? It was I plus lambda camera times y. I write down in terms of eigen decomposition looks like this. And I can write that as a sum of 1 over 1 plus lambda tj times uj transpose. No, sorry. uj transpose. What's that? It is uj transpose, right. Okay, so let's look at this now. If I didn't have this term, if I just had the sum of uj transpose y, then that would actually, I claim that would be doing regression onto a set of natural kth order splines. Why? It's because the uj's are eigenvectors for k, and so they're going to have the same column space as k. And you can maybe convince yourself that k has the same column space as the natural spline basis matrix. And so if I were to do regression on the u's, it's just like doing regression on the natural splines, and this is exactly the regression fit. When I put this term here, it's like I'm doing regularized regression. We already knew that because we're doing, that's what the regulation term is doing right there, but it actually gives us a more explicit form for it. And it tells us that we're shrinking the regression coefficients by an amount that depends on lambda. We're not shrinking them equally. Actually, right, these are the regression coefficients for regressing y onto a j basis vector. I'm shrinking it by a different amount for each j. I'm multiplying by 1 over 1 plus lambda times dj. So if dj was large, I'm actually shrinking it more. If dj was small, I'm shrinking it less. So this is called, I don't know if I wrote it down, this is called the Reinsch form. That k is called the Reinsch form for smoothing splines. And these are called the Reinsch basis vectors. are the Demler, these called Demler-Rhine spaces. And there's a ton that's known about the properties of these U's. In particular, it's known, I put a reference there to the original paper, but these two authors first studied and then people kind of studied in depth afterwards, that a smaller Ej means a smoother U. And a larger Tj means a more wiggly U. And so what I mean by that is if I were to plot over its components 1 through n, or say over the positions x1 through xn, any one of those eigenvectors, you could think of it as a function, and the smaller its corresponding eigenvalue, the more wiggly it is. It's much more wiggly than the smaller its corresponding eigenvalue, the more smooth it is. And the larger its corresponding eigenvalue, the more wiggly it is. And so that's known from people studying this basis. And so what do smoothing splines do? They actually shrink more if the eigenvalue is large, so if uj is really wiggly, and they shrink less if the eigenvalue is small, so uj is very smooth. So essentially by turning up lambda, we're tuning out the low frequency components of the fit, the very wiggly components, and we're shrinking them almost effectively to 0, and we're only permitting that the lower frequency or the smoother components to pass through. By making lambda smaller, we're allowing the wiggly components to have a voice. Question?
Is this statement equivalent to what we say in PCA, that the eigenvectors corresponding to the larger eigenvalues contain most of the variance?
Well, I guess it is analogous when you say it like that.
Where we map to the space spanned by the largest eigenvectors to keep like the most variance. Okay.
I don't think it's equivalent because they can have a large variance even if if I think about the variance across the input positions, like it still have a large variance if it's just say like a linear function, but that was at a steep slope. But somehow more than that, in this case, it actually relates to the smoothness of the eigenvector. But yeah, it's not a bad thing to remember. Yeah.
You should get back to linear fit from lambda to infinity.
Yeah, I was just about to ask that. So, when lambda goes to infinity, like I said, we should go back to linear fit, right? Because here I take lambda to infinity, I say it should have no second derivative. So that means that f double prime is 0, so I have to fit a linear function. So what's happening here? I've actually been slightly sloppy with my inverses, but this is absolutely correct right here. And so what do you conclude from that? If I know that when I take lambda equals infinity, I have to get back to linear fit. I conclude that actually some number of these eigenvalues have to be 0. So k has 2 0 eigenvalues actually. The bottom 2 eigenvalues are 0. The smallest are 0, which means that you're not penalizing whatsoever towards the linear fit. You can fit a linear function no matter what. Like at 1 over 1 plus lambda times 0. As I take lambda to infinity, those terms never get shrunken away. Okay, so the easiest way to remember that is from the initial smoothing spline equation, but yeah, the bottom 2 DJs are equal to 0. So on your homework, you're gonna pull these out programmatically, and you're gonna look at them and just confirm that this behavior actually exists. Maybe do a couple of things I forget. All right, so we don't have much time left. I think I'm going to maybe take a little bit of next time to finish up nonparametrics. I cannot clearly do everything in this document, so I think I'm definitely going to do some part of linear smoothers. So we're going to I kept saying the whole time, hey, this is a linear smoother, this is a linear smoother, this is a linear smoother. Everything I was pointing is linear smoother. There's a reason for that. We'll maybe get to that conclusion. Besides that, we could talk about RKHS, or we could talk about wavelets. Whatever we pick, I'll do really quickly. So I have, I think there's not really any problem with choosing one or the other, so I'll just have to do whatever most people want. How many people want to see wavelets in adaptive progression? And how many people want to see RKHS? How many people do not care?
Or you didn't put multivariate in it.
That I'll do at the end. Yeah. I'll do multivariate at the end. Just very quickly. Okay, so I guess we'll do RKHS. Sorry, wavelets. Wavelets are, they would take a lot of time anyway, so I would do them pretty brief.